Okay, guys, so what we're going to go over right now is um, just a framework of how to solve problems in 2D motion. Now, before I get started, you guys shouldn't be intimidated by things acting now in two dimensions instead of just one dimension. These problems are all going to be handled in the same exact way as our one-dimensional kinematic problems. The only thing now is that you essentially do it twice, right? So there's one big rule here that I want you guys to keep in mind while we're doing this, right? So this is our problem solving strategy here I have on the left side. One thing that I want you guys to keep in mind during this is that I have two directions. Let's say for us this will be horizontal or X direction, okay? And vertical or Y direction. These two things, I want you to keep them separate always, all right? They are independent of each other. So for the X direction, we're going to have something like initial velocity, final velocity, acceleration, displacement, and time, right? And similar, in the y direction, we'll have the same exact variables, except they will be y, right? So you see me writing these little subscripts in. This just is a reminder for me, which acceleration am I talking about, or which initial velocity am I talking about, which displacement. This is just a marker for me. You'll notice the only thing that doesn't have a subscript here is time, because time is the only thing that doesn't care whether it's in the x or the y. Everything else is going to be strictly separate, right? So whatever's happening in the x direction is independent of whatever's happening in the y direction. The only thing that really connects them throughout our problems is going to be time. Okay? So let's kind of just see a few examples in action. Right here on the left, I have a rough problem solving strategy you can kind of use as a framework just as you're getting started, for you to approach problems, right? So you'll have some kind of motion in two dimensions, right? But we don't want to work with this in two dimensions. We want to use one-dimensional motion because that's what we already know how to do, right? So what you'll do is you'll create your two columns of variables, kind of similar, just what I've done here. You'll create this for your problem, and you'll decompose, after you fill everything in that you know from your problem, you'll decompose anything that's in two dimensions, right? So if I have some kind of vector like this, we'll call this vector v, maybe it's a velocity vector. I don't want it to be in two dimensions, right? What I want to do is I want to split this up into some x direction, we'll call this vx, and some y direction, we'll call this vy, right? So this works pretty much for any type of two-dimensional vector. So usually for our purposes here for 2D motion, it's going to be velocity, right? Acceleration is going to be a little bit simpler for us, but displacement can also be a 2D vector, right? So before we do any kind of work on this, before we use our kinematic formulas throughout this whole module, and even going further, we want to make sure that anything that's at an angle, we split it up. We split it up into x and into y. Okay, that's going to make this much easier for us. So once we do this, then we have some variables in x, some in y. Remember, they're connected by time. And then we just use our kinematic formulas that we already know from the previous lesson, right? So we'll take those kinematic formulas and we'll work with them. We'll find out the missing pieces of information, anything we're trying to find. And if we need to, at the end, what we're going to do is we'll combine them back, right? So at the end, maybe I'll have some final velocity, right? So here, I'll kind of make a note. What if at the end of this, I was able to find some new, or you know what, I'll write these kind of by themselves. I have, at the end of my problem, maybe I'll have some new final velocity in the x, and maybe some new final velocity in the y direction. Okay, so this will actually give me my final velocity vector, right? So what I need to do at the end, let's say I've solved some problem with this initial condition, okay? And then what I've done is I've solved it, and now I have some final components, some x component, some y component, and I'll use that to find my final velocity and my direction, my magnitude, remember it's going to be the length of this, the amount, and my direction of my 2D vector now at the end. So once we're done using all of our kinematics on this, then we can go back and we can put them back together into 2D. Okay, so it'll be sort of, we start with 2D, break it up into its pieces, work with it, do all the formulas we need to do. At the very end, put it back together. Okay, make a triangle and put it back together. So let's go ahead and see how this works in action, right? So what we're going to do first, this first example here is just kind of working with vectors in a 2D scenario. So we're not actually doing kinematics here yet. All we're going to do is we're going to work with vectors just so we kind of review the vocabulary that we're using here. So this first problem here, I have a ball that rolls down a hill at an angle of 20 degrees below horizontal at some velocity, right? Here's 17. So I want to know what the horizontal component of this ball's initial velocity is, okay? So let's kind of, like we discussed earlier, we're going to draw a picture here so we keep track of what's going on. Okay, so let's say we have a ball. It is rolling down a hill, and here I'll draw this a little bit higher so you can see, but there's actually an angle of 20 degrees that we have from the horizontal. So this is what below horizontal means, 20 degrees below horizontal. It just means starting from the horizontal, go 20 degrees downwards, right? So starting from the horizontal, being here, we're going to, let's go ahead and undo this. We are going to go down 20 degrees, and that's our slope, right? So this ball is rolling down a hill. We know the angle, right? So what I want to know is, okay, I also have its velocity, right? So I can go ahead and I can annotate this picture right here, but I'm going to leave it alone right now just so it doesn't get too crowded. But I know the velocity of the ball, okay, and the angle, and that's it. So what I'm looking for is the horizontal component. All right, this is super important here. We're going to keep this in mind. This is the horizontal component of the ball's velocity. So let's go ahead and see how we do this. So I have a triangle that I'm going to draw. One is my velocity. Okay, here, this has an angle of 20 degrees. Okay, it's essentially, I'm just drawing this scenario again, but without the ball and without, all of that stuff, just as a triangle so we can work with this, right? So I know my angle, and I know that this right here, let me go ahead and move this over. This is going to be equal to 17 meters per second, okay? And I want to know what the horizontal component of the velocity is. So that is actually this right here. What is this? Okay? So I know two things. I know my angle, I know my hypotenuse, and I want to find here the adjacent angle. So this is why, remember, it's very useful to use terms like adjacent instead of A, B, and C kind of sides of our triangle when we do this. So I want you guys to think about this. I'll give you a little bit of a challenge here. Look at your formulas for trigonometry that we kind of studied earlier, and I want you guys to see which one are we going to use. So let's write down everything we know here. We know velocity. This is 17 meters per second. My angle is 20 degrees. Actually, I can put this as negative 20 degrees, and I'll show you why right now. we can do this. But either way, if you do 20 or negative 20, it doesn't really matter, as long as you make this picture, this visualization. This will kind of tell you a little bit. And the thing that we want to know is right here, what is v of x, right? So again, kind of like we did in our vectors homework, I know my hypotenuse, my angle, I want to find the horizontal side. Which formula do I use? Okay, so go ahead and try to work this out, and then we will go through this together. Okay, so hopefully the formula that you came up with here was my cosine of theta, okay, is adjacent over hypotenuse. Another way to write this, okay, for us would be Vx over V. So we have this. All we have to do is fill in everything that we know. Since I'm looking for Vx, I can just multiply both sides by V, and these will cancel, and Vx will be by itself. So what we'll end up with here is Vx is equal to V cosine theta. Okay, so this is actually 17 times the cosine of negative 20 degrees. And that's it. That's how we'll solve this right here. So let's go ahead and get ourselves a number here just to make sure that we are on the same page. So go ahead and do this in your calculator as well. I have cosine of negative 20 degrees. This actually gives me 15, out here I'm going to put 16 degrees. So this is about, sorry, not 16 meters per second. About 16 meters per second. Okay? So, all right. Here, this is kind of showing you a little bit of work that we do with vectors. Now, an alternate way to look at this is, what if I give you the components and I ask you for the magnitude and the direction, right? So this kind of covers one example of what you might do to find a horizontal component or a vertical component to split up some vector into its components. But at the end of the problem, remember, at this step of the problem where we need to combine x and y components back into 2D, okay, we're going to need to put them back together. So that's what we're going to do here in part B. So let's say sometime later the ball changed, the hill changed, whatever. Now we have new components. So we have Vx and Vy. It's already written here for you. We have Vx and Vy. The thing that we are trying to find, okay, I can even call this V final x and V final y just so we don't get confused with what we had earlier. What is my new vector V final, right? So essentially, okay, I know V final x is 8. And here I'll kind of write this to the right and downwards for y. It's downwards because it's negative, right? So my V final in the y direction is negative 4. So what is this vector right here? This is what we're looking for, okay? So again, this time we don't have our angle. We don't know what our angle is, but we're not looking for this, okay? All we know is we know one side and another side, so we know opposite and adjacent. We're trying to find hypotenuse. There is one formula we can use to reliably find this, so I want you guys to choose that formula, and then we'll do this together, okay? So take a moment, choose the formula, and then we'll work on this together. Okay, guys, so hopefully you were able to choose our formula of the Pythagorean theorem, which is a squared plus b squared equals c squared. So just kind of showing you how we put this into action here for our vectors. It is actually vfx squared plus vfy squared is equal to v squared, right? So again, all I need to do here is plug in the values that I have for my x component and my y component, and I can use that to find v. But v is not quite by itself, right? We have this little square, we've got to get rid of it. So make sure before you do this, okay, we actually square root both sides in order to cancel that square. So now what we'll end up with is v is equal to the square root of v of x squared plus v of y squared. Okay, so now plugging everything in, all we have is, I'm going to put 8 squared plus -4 squared. So make sure if you type this into your calculator, we have this little -4 in parentheses so that it doesn't get left out. So you won't have -4 squared, right? Because calculators will tend to do that. So make sure you put this in parentheses if you put this in your calculator. And what we should end up with here, I'll go ahead and calculate this for us here, is about 8.94, okay? So my V is equal to 8.94 meters per second. This is the magnitude of this velocity, this new velocity. The magnitude of it is 8.94, okay? And the last step, guys, so remember, when we combine this, we've taken our components and we've found the hypotenuse. Now, all we need is this last little piece of information. I want to know what exactly is the direction. Those two things I'll always ask you pretty much together because they're linked very closely. What is the magnitude? And, here for C, what is the direction of this ball, right? So, here, last step, because we know all of the sides of our triangle, okay, I'm going to draw my triangle right here. Or you know what, I can just copy this over. Okay, so we've got our triangle right here. And we know now that this is 8.94. I'll go ahead and just rewrite this. I have my V final is 8.94. Okay, so I know all the sides of my triangle. Now what I'm trying to find is theta. So because we know all of the sides of our triangle, we can use whichever trigonometry function we want. We can use sine because we have opposite and hypotenuse. We can use cosine because we have adjacent and hypotenuse. And we can use tangent because we have opposite and adjacent. The only thing that's really important here, guys, is that you guys remember or correctly identify which one of these is which, right? Opposite is opposite of my angle, okay? Be careful. So if you switch these, you'll get the wrong answer. So opposite is opposite of my angle, adjacent is adjacent to my angle, and hypotenuse. So the one that I'll use here, because we already used cosine earlier, and I kind of like to use it, I'll use tangent. So let's say here, I'm going to say that tangent of theta is opposite over adjacent. Okay, and then here for our triangle, what that means for us is VFY over VFX. Okay, so when I plug this in, what I'll get is, just from my triangle by looking at it, VFY is -4 over 8. But there's a problem here. Yes, I have, okay, tangent theta is equal to -4 over 8. I'll just write that here, -4 divided by 8. That's good that I have this, but I need theta by itself. Remember, it can't be attached to this little tangent. So what I need to do, okay, kind of move this over just a little bit. You'll see why I'm going to move this over in a bit. But I need the theta by itself. So what I'm going to do is tangent inverse of both sides. Remember, this is kind of what we discussed when we first introduced vectors, is how we do this, right? So if we take the tangent inverse of both sides, the tangent and the inverse will cancel on this side, and it'll remain on the other side. So this theta is just equal to the tangent inverse of -4/8. So here, tangent inverse, -4/8. Now we'll just use our calculator to tell us what this is. So here I'm going to do this, and if you don't get the same answer as I do, you just want to check that your calculator, whatever calculator you're using, is in degree mode, right? So if you get, let's say, a very small answer, like 0 point something or negative point something, then you want to check to make sure that your calculator is in degrees. The answer that I have here is -26.6 degrees. Okay, so again, you see this negative here. What does this mean for us, right? So we have our answer. Let's go and box this. But we have this negative. What does this mean? This just means from the horizontal, I'm going downward, okay? So I'm going down from the horizontal. This is below the horizontal, okay? And that's it, guys. So we've just run through just a quick example of decomposing a vector and also getting components and putting them back into a vector. So this will come in handy when we're doing our 2D motion problems. What we're going to do next is we're going to look at a full problem with kinematics involved. So this next problem here we're going to look at is going to have kinematics involved. So that's what we'll do in the next video.